How long are you going to talk about, approximately?
50 minutes, 1 hour, something like that.
Uh-huh.
All right. Is that fine?
Fine. Let's start.
Okay.
Start.
Okay. So so Riccardo and I have this joint paper, which, as I said, is the first time that we present. So it's very experimental. It's very much a work in progress. We have, and also we really appreciate the opportunity of presenting it here and having your thoughts about it. And the general, so let me share my screen so that you hopefully can you see? Can you see my screen?
Yes, Lorenzo.
Perfect. So let me just make sure that this goes full screen. Okay, so as I said, it's a very experimental talk, and the topic is a combination of truth theories and theories of vagueness. So in particular, as you see, what we are going to try to do is to provide a framework to treat the semantic paradoxes and the paradoxes of vagueness, the theoretical paradoxes, in a unified way. Okay, so this is the menu for today. We will introduce the naive approaches to truth and vagueness, which are the ones that are supposed to generate the paradoxes. Then we are going to discuss the paradoxes themselves, and then we are going to present the paradoxes in the framework of three-valued logics, in particular in 4 three-valued logics, 2 fully structural and 2 substructural, which are basically the test case, the case study for our formalization. Then we're going to introduce a variation on the theme of standard semantic paradoxes and theoretical paradoxes, which in the literature go by the name of revenge paradoxes and high-order vagueness paradoxes. And finally, we will say a few words on how we are proposing to identify these paradoxical phenomena. So let me start straight away with the naive approaches to truth and vagueness, and many of the things that I will say, especially at the beginning, might be very well known to many of you. In that case, I just ask you to be a little bit patient. So I start from a rehearsal of plausible yet problematic truth theoretical principles. So the principles that you see on the screen, the T-schema or the naive rules for introducing and eliminating the truth predicate, are the famous principles that are often thought to characterize naively the truth predicate. So if we want to have a predicate that expresses the concept of truth in the object language, then one of the intuitive things that we want our predicate to do is to satisfy the truth schema. So the equivalence between a sentence phi and its truth predication, true phi. Similarly, we might want inference rules that characterize the truth predicate to the effect that whenever we derive phi from premises gamma, we can derive its truth predication, phi is true, and vice versa. Whenever we derive that phi is true from a set of premises gamma, we can derive phi. There are alternative characterizations. You might think that these are all equivalent. They're not entirely equivalent in the non-classical logics we are going to consider. So I haven't said yet what this notation is. You can think of some sort of name for phi in a fixed coding, like if you have an arithmetical setting, it can be a Gödel coding or something similar to it. Just the name of phi, simply because the notion of truth is formalized as a predicate, so predicates apply to terms. Okay, good. So this is the idea behind transparency, and the requirement of transparency, or sometimes also called naivete, is very widely discussed in the literature, and it's considered to be very well motivated, mostly on linguistic grounds. In particular, if we reflect on the behavior of the truth predicate using our own linguistic competence and ask ourselves what kind of principles, axioms, or rules should the truth predicate obey, then these principles appear to be particularly natural. On the other hand, one of the main motivations in the literature, especially on the literature on truth theoretical deflationism, is that principles such as the ones that we have just mentioned seem to be required for the truth predicate to perform its role in inferences and reasoning. So in particular, there seem to be kind of certain kinds of inferences, for example, that express agreement and disagreement with infinite sets of sentences, that in order to be faithfully modeled require principles to the effect that we can introduce and eliminate the truth predicate freely. So I'll not say more about this, but feel free to ask me questions. But this is just it's just to summarize the two main kind of motivations that are discussed in the literature for these naive truth theoretical principles. Okay, so the other main actor in this play instead is the notion of a vague predicate, and in particular the main principle that is supposed to govern the semantic behavior of vague predicates that goes under the name of tolerance. So if you have a vague predicate P, consider tall, for example, and you have that S is P and T is extremely similar to S as far as P is concerned, which you formalize with this tilde subscript P, then T is P as well. So for example, if John is tall and Sam is extremely similar to John as far as the height is concerned, so let's say that the second person is just 1 millimeter shorter than the first person, then the second person is tall as well. And this seems pretty intuitive. And again, just like in the case of the naivete or transparency requirement, there are many ways in which this principle can be formalized. In particular, linguists working on vagueness tend to distinguish between the collective reading, which would correspond to the universally quantified axiom, or the distributive reading, which is just a collection of all the instances of the axiom. Finally, we can also have a rule, we can also have a meta rule, and as I said, I will not say very much on the different possible logical formalizations, but they are relevant when it comes to formalizing these principles and validating these principles in non-classical logics, for example, logics that might not have a strong conditional. Okay, so as I said, the naivete requirement for truth is motivated mostly by philosophers and logicians based on some reasonings and inferences that we want to formalize. Instead, the tolerance principle is widely motivated by looking at linguistic and psychological evidence. There's a lot of empirical work done on tolerance, especially for perceptual predicates, such as predicates, vague predicates, obviously expressing colors, and so on. And it really seems that many speakers implicitly conform or implicitly adopt some form of tolerance when applying vague predicates in everyday uses of language. And what we're going to do here is attempt, as I said, to unify these two principles, transparency on the one hand for truth and tolerance on the other. And this is just to anticipate what's going to happen later, but we're going to unify them via appeal to what we call an indiscernibility principle. So the principle we're going to invoke and basically use to argue that tolerance and transparency are basically just two members of the same family is the principle that you see highlighted on the screen right now. So basically, whenever you have this binary relation tilde on terms and two formulae phi of x and phi of y, so same formula of x and y, then we postulate, so the principle postulates that whenever x and y are sufficiently similar according to the similarity relation tilde that takes the place, of the symbol tilde in that scheme, then phi of x is equivalent to phi of y. So we'll have occasion to say more about this particular principle, but you can already see, well, a couple of things really. One is that tolerance is really close to this principle. Tolerance is a form, we can say, of indiscernibility. And the other one is that this principle is reminiscent of the converse of Leibniz principles. So this principle over here that says that whenever two things are identical, have exactly the same properties in one of the most famous ways of glossing the converse of Leibniz's law. There are differences, of course. Well, our schema is a first order schema, whereas the converse of Leibniz's principle is a second order axiom. So Leibniz's principle quantifies also over collections which might not be first order definable in the full semantics for second order logic. And also so this is clearly more powerful if you assume the full semantics for second order logic. And also our principle concerns an arbitrary binary relation, whereas the converse of Leibniz's law is about identity. Whereas here we are just giving the very general form of an indiscernibility principle concerning some binary relation which we should informally understand as a form of similarity. Okay, so These are the main constituents of what we're going to say: truth and its naive principle, vagueness, vague predicates, and the naive tolerance principle, and they are going to reappear again as instances or forms of a more general indiscernibility relation. So in order to actually present the principles of naive truth and tolerant vagueness and their effect, we are going to introduce a formal language and framework where we can actually talk about the truth predicate and vagueness predicates and vague predicates. This framework is rather standard for both the truth theoretical part and the vagueness theoretical part. It's simply that these kind of languages are not often merged, as it were, and used simultaneously. So this might be a bit puzzling at first, but it's really just the essentially result of putting together the standard linguistic assumptions that are employed to model truth predications and the ones that are used for vagueness. So in particular, let's use a first order language, L of TV, that includes a unary distinguished predicate, TR, which we are going to use to model truth, and many unary predicates, P1, P2, and so on, which we are going to use to model vague predicates. We limit ourselves to unary vague predicates. There might be, of course, non-unary vague predicates. We only limit ourselves to this to simplify. We also include constants that are associated with each of the vague predicates, just to simplify the presentation of theoretical series, as we will see later on. And then, of course, we add the similarity as far as PI is concerned. So a relation that expresses that two individuals are similar as far as the application of the vague predicate PI is concerned. So two people that have similar height, or two colors which are two patches of color that have a similar shade of color, something like that. Finally, we need some technical requirements which are really not particularly interesting per se. We just need them to make sure that we can carry out the model theoretic constructions to follow. In particular, we need an acceptable and, for simplicity, countable model of that language, so that for every individual in the support of the model, there is a constant that designates that individual in the model. The acceptability requirement is just a technical requirement that makes sure that the coding of syntax is definable in the model, so that we can have a well-behaved coding machinery that enables us to model truth predications. So nothing deep. The other thing, of course, is that we have closed terms for the result of coding formulae in the language, so that whenever you have a formula phi of the language, then this expression here is a closed term that belongs to the language and that denotes, in the target acceptable structure, the code of phi. Okay, finally, we also assume what is sometimes called in the literature strong diagonalization. We cannot do with a weak diagonalization, because the usual diagonalization formulated with the biconditional, because we are going to discuss logics that do not have a good biconditional. So for every open formula phi of x, we assume that there is a diagonal term, so a term t of phi, that in the target model denotes the same object as the code of phi when x is replaced via that diagonal term t of phi. Okay, as I said, this is just some very standard setup to make sure that we can actually correctly model truth predications, mostly because for the vagueness part, we don't need anything of the sort. Okay, I think I have commented already on the main aspects of the technical requirements. In particular, this is something that I have said already. Oh yeah, also in order, the requirement that the language has content for each element of at least one countable acceptable model is just a simplifying requirement to dispense with variable assignments, because we have terms for elements of the model. Of course, we could complicate things and introduce variable assignments for the model theoretic constructions we're going to discuss. And the last requirement, as I said, actually ensures that diagonalization, a form of diagonalization, holds in systems that might not have the classical biconditional. So in particular, suppose you want to reason about a liar sentence, so a sentence lambda which is equivalent in some sense to a sentence not true T lambda, where this term T lambda here is a diagonal term in question. Well, the form of diagonalization that is going to hold in all the logics and theories that we're going to consider is the meta-inferential form of diagonalization that you see on the screen right now. So whenever you have an inference of you infer lambda from gamma, you can infer the equivalent not true T lambda from it, and the other way around. But you might not have the biconditional, and you might not have the single inference. So you might not have lambda turnstile not true lambda. The meta inference is guaranteed to hold in all the systems you're going to consider. So this is just to make sure that we can model essentially the liar paradox and every other semantic paradoxes that we want. Okay, good. So this is by way of setting up. Now, the principles for, first of all, if you have questions, I don't see all of you here on my screen, but if you have questions just like on what I have said so far, just let me know. So I'm not entirely sure that I will see you if you raise your hands, but if you just unmute yourself and say something, I'll hear you.
Lorenzo, I'm checking the list of participants, so everyone who's wishing to ask a question can just raise the hand over there and I'll see it.
Perfect. Thanks so much. Okay, so the principles that we have just introduced for truth on the one hand, naivete, and for vagueness on the other, tolerance, are known to generate paradoxes, in particular semantic paradoxes like the liar paradox, Curry's paradox, and many others on the one hand, and theoretical paradoxes on the other hand. So let's briefly review these paradoxes in turn, because we are going to need the paradoxical reasonings later on when we are going to subject them to a further formalization. Okay, so this is one way of informally or rather semi-formally present the liar paradox proof theoretically. And you can see paradoxes in two ways. On the one hand, as derivations of contradictions, and in particular in logics that have ex falso quodlibet triviality, so a proof of every sentence whatsoever, or model theoretically as a proof that a certain evaluation function or a certain model does not exist. So here, for example, you assume a sentence lambda which is equivalent to non-true lambda, equivalent in the sense that you have just seen, so in this sense here, that you can infer non-true coded lambda from lambda and the other way around. And if you have classical logic and the naive principles for truth, you can easily see that you can infer every sentence whatsoever. And as you will see, we use, in order to derive the trivial conclusion, namely a proof of phi from no premises for any phi whatsoever, we see that we actually employ a lot of principles. In particular, we use reflexivity, which corresponds to the assumption rule in standard natural deduction. We use, of course, both the truth elimination principle and the truth introduction principle, and we use both introduction and elimination rules for negation. Other structural rules that we employ are structural contraction and cut. The passage here corresponding to definition of lambda is exactly the diagonalization step that I was mentioning before. This framework here that you see is basically a natural deduction calculus presented in sequence style, following very roughly Greg Ressel's formalism in his book on substructural logic. And it's kind of useful to use this kind of framework because we can see very clearly where the structural rules are used. And in particular, it's important to have in mind that all these ingredients are actually employed, in particular reflexivity, negation elimination, negation introduction, contraction, and cut, because amongst the various families of logics that have been proposed to address the paradoxes, we find exactly non-reflexive logics, non-contractive logics, non-transitive logics, and logics that do not have the introduction rules for the negative connectives, like negation and conditional, and logics that do not have the elimination rules for them. We're going to talk about 4 of them. So minus the non-contractive logics, we're going to talk about all of them. Okay, so as I said, semantic paradoxes proof theoretically can be seen as proofs of triviality, and model theoretically they can be seen as non-existence proofs. In particular, a proof that there is no classical model that validates naivete. So, non-surprisingly, there is no classical model where the unrestricted Tarski biconditionals phi, if and only if phi is true, are validated. Or equivalently, there is no classical evaluation V such that for every sentence phi, it assigns to phi the same value that it assigns to phi is true. The proof is extremely simple. We just consider the liar sentence equivalent to not true lambda, and we try to assign it a value. We suppose that we actually can evaluate it classically in accordance with this requirement here. Well, since we are supposing that we can evaluate the liar classically, it either has value 1 or value 0 in a fully classical evaluation. But if it has value 1 and we also have the naivete requirement satisfied, then also not lambda is supposed to have value 1, which is impossible in classical evaluation, or in any evaluation function really. And the same conclusion holds, of course, the same absurd conclusion follows if you suppose that, sorry, that's my antivirus. The same absurd conclusion follows if you suppose that lambda has value 0. So if you try to give the liar sentence value 1, it ends up having value 0. If you try to give it value 0, it ends up having value 1. So there is no way of giving it value 1 or 0 if the evaluation is classical. And it also obeys naivete. So in this case, we have a non-existence proof. This is just to sum up what I have just said. Semantic paradoxes can be presented in these two ways. Theoretical paradoxes, the paradoxes of vagueness, can also be presented in two ways, but they typically present much less variety. So semantic paradoxes are a wide and diversified family. You have the liar paradox, Curry's paradox, McGee's paradox, many other antinomies that involve semantic notions, whereas the paradoxes of vagueness pretty much all obey the same pattern that goes back very many centuries and takes this name. So theoretical paradoxes for one instantiation of this pattern, which is the paradox of the heap. So if you have a huge number of grains, they form a heap. You take one out, presumably the resulting number of grains still form a heap. You take one out, you still have a heap. So at each step, you always have a heap. But at some point, if you carry on, long enough, you end up with no grains whatsoever, or with one grain of sand, or what have you. And clearly, you don't have a heap anymore. Well, basically, the very same patterns, the very same pattern reproduces itself for all the vague predicates. So you can start with the really tall person, then consider the next person in line, which is just 1 millimeter shorter, and that person is still tall. Then you go down, 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 only by 1 millimeter, you end up with a clearly non-tall person. And this, what you see on the screen right there, is basically a simple formalization of this reasoning pattern. You start from a clear case of the predicate P applying to some individual constant. So like a person who's very tall, so let's say John is 2 meters tall, and clearly the predicate tall applies to him. Then you consider another person which is very similar as far as the predicate P is concerned, so another person which is just 1 millimeter shorter than the first person. And well, this is just conjunction introduction. Then if you have tolerance, if you have the tolerance principles, namely that the application of vague predicate supports minimal changes, so that whenever you have x and y minimally similar as far as P, you can go from P of x to P of y, then you have this particular instance here, the instance involving the really tall person we started with, C0, and the next person in line, C1, so you conclude that actually C1 is tall. Now, this seems no problem if you just declare that one person who's 1 millimeter shorter than a 2 meter tall person is himself or herself tall. This is fine, but the problem, of course, is that if you carry on enough, then basically you declare any person whatsoever to be tall, and that seems intuitively wrong. So you end up by declaring that Cn, which we are assuming is clearly non-tall, is in fact tall. You can also formulate the theoretical paradoxes model theoretically. Again, this is just a proof that every individual in the kind of domain we're considering is actually tall. So you just show basically by reproducing the previous reasoning that if you accept the tolerance principle, you end up declaring anyone tall, and by the same token, you declare everyone short and everyone rich and everyone poor for whatever vague predicate you want. So obviously we end up with the contradiction if we actually assume that there are clear-cut cases of tall people and clear-cut cases of non-tall people. Okay, good. So as I said, this is essentially just a recap of what I said before. Theoretical paradoxes are typically identified in a more stringent way. They all conform to this pattern, and they can be also identified proof theoretically or model theoretically. To see how am I doing with time? Not great. So I'm going to introduce the three-valued logics that constitute the case study of our work, because, as I said, we are going to try to offer a unification of these two kind of paradoxes, but in particular, we're going to study how these paradoxes play out in a specific environment, which is widely discussed in the literature since 1975 at least, and this environment is three-valued logics. So let's talk about naive truth in three-valued logics and vagueness in three-valued logics. We use the synonym partial here, which is sometimes found in the literature as well. Okay, so what is a partial model or three-valued model? Is just a very simple generalization of a classical model. So rather than having essentially a set serving as a support and an interpretation function for atomic sentences, for atomic formulae, that sends them to the value 1 or 0, you just have a function that sends them to three values. So rather than having just the classical false and the classical truth, we also have an intermediate value, a half, and we use these numerical representations because they make it easier to express the evaluation clauses. So super simple. Rather than a classical evaluation for the atomic formulae, a non-classical one which features an extra truth value. And we can immediately extend this evaluation for atomic formulae to complex formulae by using the so-called strong-Kleene evaluation. So basically, the atomic case is provided by the target model, just as in the classical case. And if you see there on the screen, the value of complex formulae is given by algebraic expressions which are exactly the same as the classical case. They just end up with different outcomes because we have a larger value space that includes the value half. But the value of the negation is 1 minus the value of the negand, just like in classical semantics. The value of a conjunction is the minimum of the values of the two conjuncts, like in classical semantics. It's just that now we also have the value of half around. The value of the universally quantified sentence is the infimum of all the instances. We are using, for simplicity, substitutional interpretation of the quantifier because we made sure that we have enough constants for elements in the domain. In the three-valued case, we could use the minimum there as well. The infimum is just more convenient when you generalize this to partial semantics, which are defined in more complex value spaces. Okay, so evaluation clauses, they are just the classical ones, but with these three values. And once we have these evaluation clauses and partial models around, we can actually define two notions of truth that are going to be used to define four logics. In particular, let's say that a sentence is strictly true, given a certain model M and an evaluation E based on that model, if it has value 1 in that model, in that evaluation. And it's tolerantly true if instead it has value half or 1. This terminology is taken from a seminal paper by Pablo Cabreras, Poligray, David Ripley, and Robert Van Roy, where they use this way of cashing out the difference between strict and tolerant truth to actually capture different notions of validity, which is exactly the next definition. So you can basically construct a generalized notion of validity, which you might call MN validity, whenever you have essentially all the sentences in the premises which are n true, and all the sentences in the conclusion, we have just one sentence here, which is n true. So we can formulate a notion of validity which is strict. So whenever all the sentences in the premises are strictly true, so they have value 1, so does the conclusion, or that is tolerant, so that whenever all the sentences in the premises are tolerantly true, so have value 1 or a half, so does the sentence in the conclusion. Or we can mix things up, so we can go from strict truth in the premises to tolerant truth in the conclusion, or the other way around, from tolerant truth in the premise to strict truth in the conclusion. So this is essentially the way in which we formulate 4 different logics. The strict logic is defined as preservation of value 1 from premises to conclusion. So it's just a classical notion of validity, but now we have a value space with 3 values, so it will be extensionally different. The tolerant logic instead also, by the way, strict logic is the same as strong linear logic K3, as is often called in the literature. The tolerant logic, on the other hand, is the same as LP, the logic of paradox, and is the logic defined as preservation of value 1 or a half from premises to conclusion. And then TS and ST are the mixed ones. So in TS, an inference is valid whenever it's the case that whenever the premises are tolerantly true, the conclusion is strictly true, and ST is the other way around. Whenever the premises are strictly true, the conclusion is tolerantly true. Now, these logics have widely different behaviors between them. In particular, strict logic is one of the logics that I said before do not validate the introduction rules for the negative connectives, negation and conditional, validates the elimination rules for them. So you don't have the conditional introduction, but you have modus ponens, and is a fully structural logics. On the other hand, the tolerant logics presents the opposite behavior. You don't have the elimination rules for the negative connectives, but you have the introduction rules. So you don't have modus ponens, but you do have conditional introduction. And finally, these 2 logics are substructural logics. TS is non-reflexive and ST is non-transitive. So reflexivity doesn't hold in TS and cut fails in ST. There are further differences, but these are the main ones. So I'm going to skip the next slides where we are supposed to discuss these logics in the interest of time. Okay, so now that we have these 4 logics, let's see how naive truth and vagueness is modeled in them. And so the way in which we model naive truth is semantically by reproducing the treatment. So these 4 logics are applied to the case of truth and developed into full-fledged theories of truth by considering the development, well, the model theoretic construction, which is called as Kripke's construction. So how to describe Kripke's construction informally? Well, the idea is actually extremely simple. You start from a model of the base language that doesn't include any evaluation for sentences of the form per phi, and then you gradually build the extension of the truth predicate. Remember, the truth predicate is a regular predicate, so it has an extension just like any other predicate, in stages by looking at what was validated by the model at the previous stage. So basically you have a jump, okay, that extends the previous stage of the extension of the truth predicate. So let me guide you through this by ways of examples. So suppose you have a sentence psi, the one you see highlighted there, that is in the extension of the truth predicate at a certain stage in your construction, okay? Then clearly if psi is true, then intuitively also the result of putting a double negation in front of psi is true. So whenever you have psi in the previous stage, alpha, you have not psi in the next stage, alpha plus 1. And the same goes for essentially all the results of considering logical combinations by preserving value 1 in the strong linear evaluation that we have seen right now. This one is the version of quick construction that employs the strong clean evaluation for logically complex sentences. Other versions are possible. So again, by way of example, if psi is in the extension of the truth predicate, so it's true, and chi is in the extension of the truth predicate, so it's true, then the conjunction is true as well. And instead, if at least one between phi and psi is such as its negation is true, then the negated conjunction is true as well. And you go on like this in stages, essentially corresponding to applying this jump operation as many times as possible until you have evaluated all the sentences that can be so evaluated in your language. The only other thing I want to draw your attention on is the treatment of the truth predicate, which is very unsurprising because we want to validate a form of naivete. Remember the intuition that phi and phi is true are somehow equivalent. So whenever a sentence psi is declared to be true, so it's its truth predication. So that you start by accepting the sentence 0 equals 0, so your model validates that. Then the sentence 0 equals 0 is true, is accepted by your model. Then the sentence 0 equals 0 is true, is also accepted by a model by considering iterations of the truth predicate, and so on. Okay, so this is the Kripke jump, or at least the very compact explanation of that. I hope that was sufficiently clear. I'm happy to, I know this is rather quick, but otherwise this is just a setting up. Otherwise we don't get to the more innovative part. And the way we use the Kripke jump to actually construct a model is that we start from a model whose interpretation of the truth predicate is completely empty. So we start from a model which has a domain, has an interpretation for all the rest of the vocabulary, and has an extension of the truth predicate which is completely empty. Okay. Then at stage 1, we put in the extension of the truth predicate the names of the sentences which are true in the model. It's the previous stage, so the sentences which are true in the model you see highlighted over there, which obviously do not include the truth predicate. And then you generate a stage alpha plus 1 by closing the previous stage, well, essentially by considering the union of the previous stage and the result of applying the Kripke jump exactly once. At limit stages, you take unions. So this is how the Kripke construction gets going. And we know that at some point, this construction goes long enough, in particular, it goes through all the recursive ordinals, and at some point, it stops including new sentences. This is just a specific instance of a more general phenomenon. But roughly speaking, the idea of why this theorem holds is that there are more ordinals than sentences. So at some point, you run out of stages to evaluate new sentences, and all the sentences that can be so evaluated by the model you're building are actually evaluated. So what is the Kripke model? Where a Kripke model is a triple of this form here, where the first two components are just a regular partial model, a domain for the model and an interpretation for the other non-true theoretical vocabulary. And this set there is a Kripke fixed point. So a set of this form, namely a set such that contains all the sentences that can be evaluated in this procedure. Okay, the typical thing that happens at Kripke fixed points is that a sentence phi is in a Kripke fixed point if and only if the sentence true phi is in that fixed point. So we have recovered a version of the naivete intuition that we started with. We know that it's paradoxical in classical logic, but going to a non-classical logic, we can actually both give a monotheoretic construction, as we will see in a moment, also a proof-theoretic implementation of the naivete idea. Okay. So, yeah, this is basically what I have just said. So every Kripke model generates an evaluation which validates the naivete requirement. So a sentence phi receives always the same value of the sentence phi t that you see on the screen, which is any result of substituting a sentence psi with psi is true within phi. So this basically is a slightly more general version of the naivete requirement. But if you keep in mind that in every such evaluation, a sentence phi always gets its same value as its truth ascription phi is true, then you have an idea of what goes on from a truth theoretical point of view in these models. Okay, finally, we can use these models to actually come up with theories of truth. So we have already 4 logics. Now we need to expand them to true theoretical principles. And in particular, we can expand the first one, the second, the third, and the fourth, so all of the 4 non-classical logics we have seen. And the way we do it is very simple. Rather than just quantifying over any partial model, we only quantify over Kripke models. So only over those partial models which in particular have an extension for the truth predicate, which is a Kripke fixed point. Great, so now we obtain 4 theories of truth, and they all validate some form of naivete. So as you will see, I will not discuss this in detail, but as you see, the ones that have a strong conditional, so tolerant, and strict tolerant logic, can actually validate the Tarski biconditionals. So clearly they're very distinct from classical logics. The ones that do not have a strong conditional, like strict logic, validate the inference from phi to phi is true and vice versa. And TS, which is extremely weak and doesn't have any valid inference and only valid inferences, instead validate the meta-inferential version of naivete. Okay, good. So this is just to quickly present how theories of truth can be developed in these 4 non-classical settings. Now, super quickly, and then I will give the floor to Riccardo. I will just describe how vagueness is treated in these logics. So let me describe the kind of models we're going for here. So before, what we had was this. We had a general notion of validity, actually 4 of them, strict, tolerant, strict, tolerant, and tolerant, strict. And then we used that to build theories of truth by actually restricting our attention from an arbitrary model to a Kripke model. Now we're going to do the same, and we're going to construct theories of vagueness by restricting our attention from arbitrary models of our 3-valid language to what we call theoretical models. And here in the slides, you have a precise definition of what a theoretical model is, but I will just give you some heuristics. And it's basically a model that subdivides, let's say, the individuals to which we consider the application of the predicate P in 3 classes, which correspond exactly to the 3 values. So essentially, P of A has value 1 if A is a clear case of the predicate P, so let's say the clearly tall person. P of B has value half in the borderline cases, so the persons which are neither clearly tall nor clearly non-tall, they're somehow in the middle. And P of C instead has value 0. So it's basically C, where P of C has value 0, just in case the individual C is clearly non-tall. Okay, so a theoretical model, we have the abstract version here, but a theoretical model is one in which you can draw a line, and the upper portion of the line is like the cases where the application of the predicate P has value 1. Then people who are less P than the previous ones are cases in which the application of the predicate P has value half, and the last portion is basically people who are do not satisfy the predicate P. Okay, I'm aware this is just very informal, but I'm happy to go back to the formal definition if you want. But just like we have done for theories of truth, we can also here actually apply the 4 logics that we have and have a theory of vagueness. So the theory of vagueness based on strict logic is again based on preservation of strict truth in theoretical models. So in all the models that treat the application of the vague predicates in the obvious way for a 3-valid semantics, and you preserve strict truth. The tolerant theory of vagueness is based on tolerant consequence restricted to these models, and the same goes for TS and ST. Now, how about, so we have seen that the other theories do respect transparency, so they essentially yield the form of naivete, and these theories here, 2 of them are actually tolerant logics, so they do validate the tolerance principle without generating a triviality, of course. And the other two instead are non-tolerant logics. So the first two, so the one based on tolerant consequence relation and strict tolerant consequence relation, validate the generalized version and all the instances of tolerance, but the other ones actually don't. Okay, and nothing changes if we go to the other principles, of course. Okay, so that's it. I will just stop now, and Riccardo will now take care of the second part of the talk. Sorry, I realized that this was sometimes a bit quick, so let me stop sharing my screen.
Just to pass me the privileges for sharing the screen.
Now I made you a presenter.
I can see, and now let me just see if I can. Do you see the screen? Can you see it?
Yep.
Okay. Okay, yes. So I start from here, and let me just, I will be quick since we have spent a lot of our time already, not because of Lorenzo's fault, but because it was necessary to introduce a lot of stuff in order to get clear with what we are going to do. The point at which we have arrived is a point at which we have a clear idea of what are the basic paradoxes we want to deal with. Semantic paradoxes on the one hand, and the paradoxes of vagueness on the other. And we have four logics that in some way solve the paradox in the sense that do not generate triviality by changing the logic, passing to a partial logic instead of a classical logic, and blocking some part of the relevant arguments. Now, the first thing to be dealt with is the fact that to the paradoxes we have been dealing with so far, there are higher order paradoxes that are built upon them. And these paradoxes are built for the sake of showing that also in the setting that solve the basic paradoxes, you might have something like a revenge paradox, or the paradox coming out again, if you want to say a little bit more of what is happening at the semantical level. So paradoxes of this higher type are called revenge paradoxes in the case of semantic paradoxes, and higher order vagueness paradoxes in the case of soritical sort of arguments. Let me just see if I can. Okay. Please, I have to shut up Andrea, who's otherwise there was a noise. So let me speak of revenge paradoxes first. Revenge paradoxes first. How are they built? Suppose you have a theory of truth that blocks paradoxes. Then the theory does what you want, does not allow you to generate a triviality, for instance, like the liar paradox. Now, a revenge argument is built by extending the theory suitably by means of semantical notions that were not present in the theory, in the original theory, and show that the very same argument, the very same pattern of arguments, of paradoxes that you were blocking in the theory come up again with respect, and now formulated with respect to the new semantic notion you have added. A very quick example can be made by making use of the liar. So the liar sentence is a sentence that, if you use a partial model, can be blocked in generating triviality because it receives no classical value. It is neither true nor false. Since it is not true, you might be wishing to express the fact that the liar sentence, which gets value 1/2, in your semantic. The point is that you cannot do it. You cannot do it because to express the fact that the liar sentence is not true, you have to be making use of this sentence here, which also received value 1/2 because of the how you have built the semantic construction. So in order to recover this sense of lambda being not true, you might be wishing to expand the original language of the theory, the language of the partial theory of truth you have formulated, by a determinately operator that recover a classical behavior for sentences that do not behave classically, in the sense of this very simple truth table that you can see. So a determinately operator applies to any sentence and returns you value 1 whenever the sentence is true, or also in the partial model, and returns you value 0 whenever it is not true. Exactly what you would like to say about lambda. So the determinately operator is introduced in the language in order to recover the possibility of speaking of lambda as not true. And in order to do that, you have to recover the possibility of speaking classically of sentences behaving not classically. The point is that at this stage, you can now reformulate exactly the paradox you have got rid of, the liar paradox, with respect to a new sentence, to a new liar sentence, which takes into account the fact that you have expanded your language by the determinately operator. And you build this sentence exactly by diagonalizing out the language exactly as you did for the liar sentence, only that you diagonalize the expanded language, and you consider this sentence lambda d to be the one that is equivalent to the sentence that says of lambda d that it is not determinately true. And then you can see, I don't go through the details of the argument, but you can see that you don't have the possibility of evaluating the new sentence with respect to the partial model. So the sentence is neither true nor false, nor gets value 1/2. Because all these 3 possibilities, and you can see briefly on the screen the argument that you can see that the paradox is recovered, by the way, all these 3 possibilities generate a contradiction.
Riccardo, they ask if you can make your screen like maybe full screen or something like that.
Okay, I have to go on Vista. What is that? Let me just try with Control. No, because Control L does not work.
Prima.
It's here. And
Modalità schermo intero.
Okay. There we are. Is it okay? Okay. So let's go on. So this is basically how to recover the liar paradox in a situation in which you have expanded your language for the sake of expressing a classical property, the classical property shared in the partial models, or in the partial models also by those sentences which are neither true or false. And you can see that you can build a new version of the very argument you thought you had blocked. So this is an example of a revenge liar. Exactly as you have a revenge liar by expanding your language with a determinately operator, you can use the very same expansion to show that you can recover also the vagueness paradoxes you had solved, so to say. So the setting is the same as the basic paradox. You assume to have a soritical series now formulated with respect to a new relation, the relation of not of being just P, but of being determinately P, because now you are interested in those relations that can be expressed in a classical way, to behave classically, in the expanded language And you can consider a soritical series, which has the same appearance of the series we had considered beforehand by Lorenzo, only that it is formulated with respect to a new relation that is makes use of the determinately true, the determinately operator. And then you can show that you cannot have both a determinately true, a determinately operator behaving in the same as the truth table we have shown, and also a principle of tolerance. Because in the same situation you were before, at some point of your soritical series, you will have an individual which is borderline, which is not neither determinately P nor determinately not P. At that point, tolerance fail, because by means of the determinately operator, you have recovered a classical behavior. So you don't have 1/2, the value 1/2. So at that point in the series, you can formulate an instance of tolerance which is satisfied, fully satisfied as far as the antecedent of it is concerned, but fails as far as the consequent is concerned. Therefore, you have results that say, well, you cannot expand a Kripke model by means of a determinately operator and save both intersubstitutivity of truth and determinateness. And in the same way, if you try to expand a soritical model to comprise both tolerance and determinateness, you have a contradiction. So this proposition summarizes the revenge paradox and the higher order vagueness paradox. You can see that revenge paradox and higher order vagueness paradox are built over a theory solving the basic paradoxes by adding one and the same ingredient, which is the determinately operator. This is used for the sake of our own unification, because the argument is as follows. If you showed that the ground level paradoxes, the liar paradox and the soritical paradox comes out from the same source, then you have already shown, by means of the construction I have just presented you, that the higher order paradoxes are constructed out of the basic one by one and the same ingredient, which is the determinately operator. So as far as the higher order paradox, no unification is needed, actually, because they are already unified. There is only one ingredient that you need to add to your language to get both versions of the higher order paradoxes, the revenge paradoxes for the semantical version and the higher order vagueness for the soritical paradox. So the point is how to unify the basic paradox. Before going into that, we need also to do something else, because for the time being, we have been able to block some paradoxes and to show how other paradoxes arise. But we don't have a setting, a logical setting, or a semantical setting in which we can express this very fact. I mean, we have seen arguments showing that you can use one of the four logics that Lorenzo presented you to block either the liar paradox, or the soritical paradox. But this very fact, the fact that the paradox is blocked, cannot be expressed semantically. You have just that argument, which is a sort of meta-semantical argument showing you that the paradox does not hold anymore. So we are going to define a setting in which the paradoxes are identified and the solvability of the paradoxes can also be formulated. In order to do that, we have to change the setting a little bit. We are basing ourselves on an idea of Lorenzo's that has been published recently in the Review of Symbolic Logic in a lengthy paper of his from 2019. And the idea is as follows. Instead of building, I'm trying to express the idea informally so that I can skip the technical details, because I don't want to waste your time anymore with other technical details. But you have to understand the point quite clearly. Otherwise, I think you will miss part of the aim we are trying to achieve. So the idea is as follows. In a normal semantical setting, you have formulas, and you evaluate formulas by assigning values in the form of numbers to these formulas. You have some values that you use some of these values to identify certain relevant semantical properties, like being true or being false, or being neither true or false, like in partial logics. Instead of evaluating formulas by assigning values, we evaluate formulas by assigning system of equations to each formula. A system of equation in our setting represent the semantical behavior underlined that lies beneath the formula. Is the semantical skeleton of a formula. And then what you try to do is not to assign values to formulas, but to solve the system of equations you have assigned to the formula. When you can solve the system of equation by assigning values to unknowns, exactly as you have learned at school to do, when you can do that, well, you have a formula that is behaving well, semantically speaking. When you cannot do that, you have a paradoxical formula. Okay, so when the system of equations you have assigned to formula has no solutions, then the formula to which you have assigned the corresponding system of equations is paradoxical. Paradoxicality is then a behavior in our setting, a behavior that follows that a certain system of equations that you have built by formulating the semantical content of a formula in an equational language, that system of equations is not solvable. This is a definition of paradoxicality that you can now reach. Beforehand, in the semantical treatments Lorenzo has presented you, you had no definition of paradoxicality at all. You had some sentences getting 1, some sentences getting 0, some other sentences getting 1/2. But 1/2 is by no means a mark of paradoxicality. Or if it is, you cannot express it in the very setting you have defined. In our case, you can define it as the non-existence of solutions to a certain system of equations. The idea of assigning a system of equation to a formula follow this intuition. This is the intuition of how to assign a system of equation to the liar sentence. Remember that the idea of a liar sentence is that the liar sentence is equivalent to the sentence expressing that the liar sentence is not true. Okay? Owing to transparency and to the construction of the lambda formula, you have that on the one hand, the lambda formula, the value of the lambda formula, the expected value of the lambda formula is the same value of the formula of the sentence expressing the fact that lambda is not true. By the way, by purely logical reason, you can expect that the value of this latter formula, the formula that says of lambda that is not true, is 1 minus the value of the sentence that expresses the truth of lambda. And this is because you have taken a negation. When you have taken a negation, you expect the negation to satisfy this equation. So the attempt you have to do when you want to evaluate lambda semantically is actually to try solving this equation that summarizes both facts. The fact that lambda is a formula that needs to get a value x that must be equal to 1 minus the value of x, owing to transparency, because the value of truth of lambda is the same under transparency of the value of lambda. Okay? So actually, this is the equation, which is not a system of equation in this case. It's just a single equation that is assigned to lambda. And this equation is built for the sake of capturing what you expect from lambda and from the behavior of lambda at the semantical level. So there is some sort of semantical intuition behind the system of equation. But this semantical intuition is somehow not is not taken into account. Is not the one that is used for the sake of assigning values to formula. What you have to do then, once you have assigned this equation to the formula, is try to solve it. And you can see that this equation can be solved over a space of values that contains 1/2 by 1/2 by assigning 1/2 to the x. And this is how you recover the evaluation semantics in the sense that Lorenzo has talked beforehand, in the attempt of solving the equation that you have assigned to a formula. So the idea behind our setting is to take the evaluation procedure in 2 steps. A first step in which you describe semantically the content of your formula by taking into account the logical form of it. So, for instance, in the case of lambda, you take into account that negation is involved. And this fact that negation is involved is used for the sake of building this equation. This equation describes exactly the behavior that you would like to have to be satisfied if you had assigned lambda a certain value, a certain numerical value. This is what the equation does. But this is not the semantical act. The semantical act is first to assign an equation to a formula or a system of equations to formulas, and then the proper assignment of values is the attempt of solving these system of equations. And then what follows is simply an attempt of doing things rigorously. But the idea is the one that I have tried to convey to you. I would not like to go into the details because otherwise we lose. I don't know if Lorenzo agrees, but at this point, since we have running out of time, there is no point in going into the details, which mimic, by the way, exactly what I've said. So what you have is that you can define a new setting for evaluation of formulas, a setting that combines an evaluation function that assigns formulas, that assigns system of equations to each formula of your language, which is the language that Lorenzo has introduced at the very beginning of the lecture. And then you have an assignment of values over the space, which is the same space of values of the partial logic, that the partial logics that Lorenzo has introduced, namely the space of values for 3-valued logic, which comprise 0, 1/2, and 1. And what you are trying to do by assigning values over this space to system of equations is trying to solve them, to produce a true arithmetical equation out of a system of equations that comprise a certain number of unknowns that depends upon the structure, the logical form of the formula. So I'm skipping these, and I only show you this slide for the sake of mentioning the fact that within this setting, we can now say of what it means for an argument to be satisfiable in the sense of the 4 ways of satisfiability Lorenzo has spoken of. It's only that in this setting, for an argument to be satisfiable means that a certain system of equation is solvable. Okay? So there is no more the problem of assigning truth values to the formulas involved in an argument. You are assigning to these formulas systems of equations, and you are trying to solve them. If you can do that, and if you can solve the system of equation assigned to the conclusion of an argument, whenever you can do it for the premises of it, then you have that the whole argument is satisfiable. Otherwise, it is not. This is the simple idea. And then you can prove that what you can do is actually to identify, as the title of this part of the talk was saying, identify in this setting both the liar, the argument representing the liar paradox, and the argument representing the vagueness paradox. And you can show, you can express by means of the semantics you have built, of the settings you can build, the fact that this is a paradoxical argument. As a matter of fact, you show that there is no way of satisfying the argument in neither of the logics we have been considering. And the same goes for the vagueness paradox, with only the possibility of satisfying it, but vacuously. And this depends upon how the notion of satisfiability has been defined in our setting. But basically, this proposition says the same as the one we had before. You have a way for identify a certain paradoxical argument by the behavior it has with respect to the attempt of assigning formulas with a system of equation and solving it arithmetically. This is the idea. And the same goes for the higher order vagueness and the revenge paradoxes. It's only that, again, due to how you have defined satisfiability, you have that both arguments turns out to be satisfiable, but only vacuously. So in a situation which is not that relevant, you can consider again the content of these propositions to be the same of the one before, of the two before. So this is now a first half of the attempt of applying, of addressing both basic ground level paradoxes of the kind of the liar, so semantical paradoxes and vague paradoxes, as well as higher order ones, by means of a unified treatment. This attempt of assigning to formulas system of equations and trying to discriminate systems of equations that can be solved arithmetically from systems of equations that cannot be solved, allow you to cover, to identify the paradoxes, all the kinds of paradoxes we wanted to talk. Now it's time to show how the paradoxes get united. And this can be done by making use of the indiscernibility principle Lorenzo has introduced. Now, the point is, try to show that both the trigger of the semantical paradoxes, namely the principle of transparency, and the trigger of the vagueness paradoxes, namely the principle of tolerance, are instances in the logical sense of the expression of this very principle, we call indiscernibility. Now, there is an easy part of the job, which is to prove that tolerance is an instance of indiscernibility, because as a matter of fact, indiscernibility is nothing but a generalization of tolerance. If you go back and see the principle of tolerance, you have that there is nothing different except for the fact that tolerance is formulated with respect to a specific similarity relation. We have to show instead that transparency is actually following deductively from indiscernibility. And you can do it by using some very simple fact from the arithmetization of a formal language. In particular, you can define a coding function, as we did, as this sort of function that assign a term to each and every formula psi of your language. When you do that, you can also define a contrary formula, a contrary function that assign the original formula to the term you have assigned to it under the coding you have defined. So call it recovering formula, because it allows you to recover the formula, recovering function, because it allows you to recover the formula out of the term that codes it. Then you can easily formulate this instance of the indiscernibility principle, which makes use of this formula. At the antecedent, you have, remember that you have an instance of indiscernibility when you have an antecedent involving a certain similarity relation and a consequence involving an equivalence, a logical equivalence between two contexts, two formulas that are formulated with respect to the terms involved in the similarity relation. And this is what happens here. If you look at it carefully, you have an antecedent where you have similarity holding of a formula psi and the formula that says of it that it is true. In particular, it holds this similarity relation between the terms that are assigned to these formulas under the coding you have defined. And then you have two contexts, two instances of the same formula that are formulated with respect, that makes use of this recovering function, and are formulated on the one hand here with respect to the first term occurring in the similarity relation, that is the code of psi, and here with respect to the second term involved in the similarity relation, the code of the formula that says that psi is true. And if you look at this formula, you will see easily, I think, that the consequent, the two formulas that are stated to be logically equivalent are easily equivalent, logically equivalent to psi and to true, the truth, the formula expressing that psi is true by the fact that you have a conjunction where one conjunct is trivially true. So the truth of the whole conjunction depends actually by the truth of the second conjunct, which is psi here, and which is truth of psi here. So you can conclude easily that this formula here is equivalent, logically equivalent to psi, while this one is logically equivalent to truth of psi, which allows you to recover deductively in an appropriate system by a modicum of basic logical passages, both the equivalence lambda if and only if truth of lambda, which is the trigger of the semantical paradox, of the liar paradox, and the version, the corresponding version formulated to the formula with respect to the sentence lambda d, which is the trigger of the revenge paradox for the liar. This shows that you can recover deductively transparency out of the principle of indiscernibility we have presented. Since also tolerance is a product of this principle, is an instance of this principle, we actually have one hidden principle that works as a root, as a deductive root for both the engine of the semantical paradox and for the engine of the vagueness paradox. Therefore, we have unified them in our sense, in the sense that we claimed. And this deductive unification allows us also to conclude that there is a conceptual unification. That is, having shown that, for instance, the principle of transparency follows from the principle of indiscernibility, it is in the principle of indiscernibility that you have to go and see what is the problem with the principle of transparency. And the principle of indiscernibility that starts from an antecedent in which a certain formula, psi, and the formula expressing the fact that psi is true are taken similar. So the idea that the principle of indiscernibility brings carries along is that it is because you are failing to see the difference between a formula and the formula expressing that the very same formula is true, that you can recover the engine that leads you to both the liar paradox and the revenge liar paradox. So by the conceptual unification of transparency and tolerance, and by having shown that these are both an instance of the principle of indiscernibility, you also get an idea of how to unify them conceptually. It is the failure of seeing fine-grained differences that leads both to the liar paradox, or to the semantical paradoxes on the one hand, and to the soritical paradoxes on the other. And since I have run out of time, actually, I would stop here and avoid going through the conclusion. We can recover them during discussion if you wish. This is basically the whole idea of the unification we wanted to present. I hope that Lorenzo agrees with me. So I'm trying to stop, okay, to go back here. Okay, so I don't know if Andrea wants to lead this part of the discussion, if there is any question, or should I do it by myself? Okay, so if Andrea is not wishing to take a lead now, if there are questions, some of you is still alive, I can see it on the screen, but the others, I don't know. Okay, I think we have a question from Rashid Ahmad.
Yeah, I have a couple quick questions. For the last similarity you presented, wouldn't that make any sentences with the same truth value be similar? So in the slide, just before the end, if you can.
I can say something, or Riccardo, do you want to go?
So in the slide before that, the deductive, yeah. So wouldn't that make, for example, psi is similar to true of phi if they have the same truth value? So then it wouldn't?
No.
Could you clarify?
Yeah, but Riccardo, do you want to say something first, or? No, I mean, the idea behind this is that it's a syntactical similarity. So the similarity holds between two sentences A and B, just in case B is the truth predication of A. So whenever B has the form A is true, then the two sentences are similar, because the idea behind naivete is that a sentence and its truth predication are similar and indistinguishable, actually, because they're equivalent or interderivable or something like that. But if B is not the truth predication of A, but it's a truth predication of C, for example, or perhaps not even a truth predication, and they happen to just have the same value, that actually same semantic value, say in some class of designated models or something like that, that actually doesn't really matter because they would falsify the syntactical similarity. So one is not the truth predication of the other. So this notion of similarity is not very informative, and it's just tailored to apply to two sentences when the second sentence says that the former is true. So it's purely syntactic, as it were.
Okay, thank you. I also have another quick question, but if there are other people want to ask first.
I think you can go on since you.
Okay, just wondering if we started with weak Kleene instead of strong Kleene, wouldn't we avoid revenge paradoxes in the first place? And why isn't that the approach? Wouldn't that be an easier approach?
So, Riccardo, do you want to say something first, and then I'll say something?
No, go.
Oh, okay, so you're referring. So there is a paper from a short paper in the JPL. I think it's the 80s by Martin and Gupta. I think the one that shows that actually you can take the weak Kleene version of Kripke's construction and close it under. I think they use something like strong negation, which is, however, interdefinable with determinacy. Is that what you have in mind?
Yeah,
exactly. So So you can close weak Kleene logics under some semantic notions that arise out of the construction. That being said, however, I just want to point out, so yes, that's an excellent suggestion, and most of what we have done here can be generalized to an arbitrary compositional semantics for the logically complex sentences. So if you wanted to take Lukasiewicz semantics, for example, adding a further conditional, or if you want to take some other many-valued semantics, you can easily do it. So this framework is general enough to basically be applicable to any compositional interpretation of the logical vocabulary. The one that does not accommodate easily is supervaluation or subvaluation. So, but yes, basically you can take any compositional interpretation of the logical vocabulary, and if you say take the resulting machine of equations and you apply as input the attempted revenge sentences, and they're not revenge sentences because they can actually be consistently assigned a unique semantic value, then the machinery would output that and would say, oh, these sentences are non-paradoxical after all because they can be evaluated. And so the resulting argument is actually from the premises to absurdity is actually non-satisfiable. So basically, the machinery remains the same, that the output changes because if the machinery as equations corresponding to evaluation clause, it has the weak Kleene ones, then it outputs that a lot of arguments to absurdity are actually unsatisfiable already. So yes, you can do that, but this answer is only partial because it only considers, of course, one form of revenge, which is the one that employs determinateness, that here we take because it's very representative of what goes on in the literature and it's very simple. There's lots of others. So I'm not sure that, by the fact that you can close the Kripke's construction formulated with weak Kleene logic under the evaluation clauses for determinacy, it follows that you can recover all the other potentially revenge breeding notions. That I don't know, but it will be something that certainly we'll have to look at, for the sake of generality. But we feel that this paper is long already.
That's right. Thank you. Thank you.
As well as it was our talk, actually. A bit too long.
Sorry.
Go on, Stefano.
I just have a bibliographic question. Okay, so this new deconnective that you use, in case of weak Kleene logics, it has been studied, actually, weak Kleene logics with this, you call it D, but Segerberg call it like plus, I think. Yeah, the bibliographic question if it's studied in some papers like strong Kleene or the logic of paradox with these additional connectives.
Oh yeah. There's a lot of that. So
bibliographic man. Lorenzo is our bibliographic man, so it's up to him to answer.
Yes, there's so for example, maybe the best overview so if you take the part 1 in Hartree Field's book, the 2008 book Saving Truth from Paradox, then you find a rather general treatment of determinateness in paracomplete logics that cover, say, the strong Kleene, that cover all the Lukashevich ones from 3-valued to continuum valued, and all the paracomplete ones. Then you can extend that in one of the later parts of the book to the dual paraconsistent logics, and they would correspond in our framework, which is Gray and Ripley's framework, and the other Cabreras and Van Roy's framework. They would correspond to strict, and tolerant. There is something about the determinateness operator in ST at the end of a paper by these 4 authors in 2012, I think. They had multiple publications of that. I think one of the classic ones is Conservatively Extending Classical Logic with Truth. It's a paper on mind. And there's a technical paper in the JPL, which is called Classic, Tolerant, Strict. And one of these 2 papers has the development of D, the determinateness operator, or strong negation, which is mutually definable with it. And I'm not aware of anything about the non-reflexive logics, the TS. So there is the development in the paracomplete and paraconsistent case and in the non-transitive case. But the non-reflexive one really is the substructural dual of the paracomplete case. So presumably you can import a lot of things sort of there.
Okay, thanks.
Well, what can I ask you? What's the Segerberg thing you mentioned? Because there's a lot of names in the literature, right? I mean, for example, yeah.
Okay, well, because you buy weak Kleene instead of strong Kleene, then you extend your language. You have negation, conjunction, and disjunction, and then if you extend with what you call D, what you obtain is what Bochvar in his paper from 29 calls Kleene external, the external calculus. Okay.
Yes.
He doesn't study it; he just introduced it in that paper. But then you have a couple of papers from Segerberg, 65 and 67, maybe, where he studies Bochvar external calculus, and then he studies modal logics of this kind of calculus. Because actually adding these new connectives is very useful when you do modal logic. I mean, when you add also modalities, because somehow, well, it's even more interesting in the weak Kleene case, because somehow you keep track of the truth values in your syntax, and there is very important because one truth value is normally read as senseless, and so I mean somehow you keep track of this.
Okay, no, that's very interesting. Thanks. So we should reference.
I can send you both the papers. They are very old, but Segerberg is very precise.
Okay. No, and this actually helps us clarifying that the determinateness operator, or this connective, which is the same by itself, if you have weak Kleene, it's perfectly fine. You don't have, the problems arise if you have also the truth predicate, of course. This is something that maybe was not completely clear from the talk, but the connective in itself is, perfectly okay.
Yeah, because another of my curiosities was what about the algebraic semantics? Because but I don't know anything when you do algebraic semantic with a truth predicate, because I mean you're talking about equations there, so I immediately thought about Kleene. I mean, checking equation in Kleene lattices at least, because Kleene lattices are, I mean the logics you're working with does not behave very well with respect to an algebraic semantics, because TT is not algebraizable at least. But I mean, there should be a sort of connection with equation in an algebraic counterpart, also very weak. Well, but I cannot formulate a precise question.
The way in which you build the systems of equations has nothing to do with the ordinary account of truth. So I mean, you're just assigning unknowns to formulas and subformulas, and then you build the equations in that way. So that could bypass the problem you have in formulating algebraically the truth predicate also.
Yes, but maybe I didn't understand where you check the validity of these equations. I mean, so this equation should be valid, should follow in some equation or quasi-equational theory, something connected to the intended logics, or
no. They are arithmetical. They are like equations. So in the paper, in the RSL paper, then I consider the general case, which is equations defined on the real interval 0, 1. So basically, you have a system of equation, and then you check whether they are true in the standard model of the real line. So basically, your meta theory. You can, if you want to explicitly formulate that as a meta theory, you formulate what Shapiro called RA. So the theory of, essentially, the second order theory of real analysis. That's categorical, so it has only one model, and so you can check whether in the only model of that meta theory, the system of equations is true. For three-valued equations, since also, by the way, you cannot define. Well, I cannot define here. Even if in this logics, even if you go to like real valued equations, you cannot define equations that only have real solutions and non-rational solutions. So actually, just a fragment of the rational numbers is fine, and then you check whether basically the equation is true in that fragment of the rational numbers. But I think something can also be said about the algebraic semantics. That's very interesting, and I don't know. I also know very little about algebraic semantics for truth theories. I think that's not the kind of semantic approach that's standardly pursued. I mean, there are these two main approaches, which is like positive elementary definitions, a la Kripke, or revision semantics. But the machinery of algebraic semantics, for some reason, is not very applied. And then I think one of the reasons might be that when you do algebraic semantics for the propositional case, then you have, it's easier, let's say, than doing it for the first order case. Whereas in the setting of theories of truth, because you have to define the coding function, you're inevitably first order. So you can restrict yourself to the propositional case, basically, if you say, well, let's consider a propositional language with name-forming device. But the name-forming device would have to have at least some features in common with an acceptable model. So we'll have to have something extra, the purely propositional case, because you don't have a truth operator, but a predicate. So because it is essentially first order or close to first order, I think this is partly the reason why people don't do algebraic semantics here, I would say.
Yeah, I mean, if you have only unary predicates, it might not be so difficult, let's say.
But it would be interesting to see it. So if someone did some systematic algebraic semantics for the theories of truth, I think it would be quite interesting. Yeah.
As far as I know, I don't think, but my knowledge might be very limited.
I don't know.
Okay, thank you, Stefano. Is there somebody else wishing to make a comment or ask a question? Well, it's late. At least you have left your PC open and on up to this time. Doesn't mean that you are alive behind that, but okay, if there is no more question, since it's almost 5 and we have...
Yeah, we can also close here, I guess.
I think we can close the session here. I don't know, Andrea, what do you think?
Yes, I think I'm sorry. I'm causing trouble. I'm causing trouble. Activating my...
There's a strong echo.
Yeah.
To me, it's fine. I mean, it was a nice paper. I think it's nice that you extend possibly this framework also to other paradoxes. I'd also to see the...
Yes, actually, what I didn't, I skip of in the last remark was a short remark about the possibility of applying this whole machinery to the paradoxes of membership in set theory, for instance, and to see whether you can make use of this principle of indiscernibility also there. For the moment, we only have this reduction for these two types of paradoxes, but we hope, of course, to extend the same methodology to further cases and possibly find some other instance.
The set theory case that Riccardo mentioned is, I think, quite natural to think about because of the fact that we can characterize, there are ways to translate between a binary satisfaction predicate, which is a simple generalization of truth, and set theoretic membership. So basically, if this is true, we can take a lot of what we have done and just import it to the set theoretic case. And the interesting thing would be to see what happens to the indiscernibility principle, which we claim is at the form of indiscernibility that we claim is the engine of semantic paradoxes, if it can also generate Russell-type paradox in the context of set. So, yeah. There is some echo.
It's Andrea, I think. Okay. So, if there is no further comment or question, I think we can just thank you for the patience.
Thanks so much to all of you for being here.
Thanks so much for being here and for participating.
Thanks for having us.
Thanks, Lorenzo, which is who's the guest, the real guest. I'm actually I'm a host in disguise, so nothing more.
Host and guest. Okay, so
thank you very much to everybody.
Thank you very much to everyone.
Ciao, grazie a voi. Ciao.
Grazie.
Ciao. Complimenti.
Grazie. Bye bye.
Ciao, grazie.
Ciao, grazie.
Ciao. Grazie.
Ciao, alla prossima.
Ciao Bea.
Ma Lorenzo, tu ora dove sei fisicamente?
Fisicamente sono nel mio ufficio a Monaco.
A Monaco comunque, ecco, sì. Questo volevo capire.
Sì, no,
mi sa che che fai? Non puoi tornare neanche per Natale?
In realtà torno, perché comunque restare qua sarebbe, lascerei i miei genitori proprio completamente da soli per Natale. Torno con tutte le restrizioni del caso, faccio il test 2 giorni prima di partire, eccetera, insomma.
Sì, immagino sarà un protocollo anche per quello.
Sì, c'è, ma è molto, molto stravagante, nel senso che devi fare il test, deve avere al massimo 48 ore di età, ma è difficilissimo avere i risultati entro 48 ore, quindi...
quindi credo dovresti...
Sono istruzioni difficili da seguire, ecco, quindi perché non ti danno i risultati. Quindi...
Ma tu puoi arrivare senza averlo fatto o deve averlo fatto in partenza?
Non c'è scritto da nessuna parte. Allora, io quello che ho fatto sono varie scuole di pensiero, è tutto molto bello, sono varie scuole interpretative. Una sostiene che sia preferibile fare il test magari 72 ore prima, ma esibire il risultato, qualche risultato, il più recente possibile. Altri ritengono che, invece sia meglio fare il test senza avere il risultato e poi avere il risultato una volta in Italia. Io poi non lo so se mi fermano all'aeroporto a Peretola e io ho o non ho un foglio completamente scritto in tedesco con scritto che il test...
Secondo me l'idea è che una volta arrivato tu comunichi di essere arrivato, ma sicuramente a nessuno che sta lì all'aeroporto ad aspettarti, lo dovresti comunicare all'ASL e poi devi infilarti in quarantena per 14 giorni.
Se sei positivo, chiaramente, perché se torni prima del 20 la quarantena non è solo a partire dal 21 compreso. Quindi per quello c'è tutto questo difficile equilibrio.
No, ma non se sei positivo, credo che la quarantena ci sia per chiunque torna dall'estero.
Cioè per chiunque torna dall'estero, ma solo a partire dal 21, non prima. Io infatti torno il 19 proprio per evitare questo. Se te torni il 21 o dopo, questo è l'ultimo di CPM.
Ah, ok.
C'è un pezzo scritto con nazionale all'estero. Torni dopo il 21.
Va bene.
Vai,
Ragazzi.
cari, allora a presto.
Grazie mille di aver resistito.
A presto, grazie a tutti. È stato un
Lorenzo,
piacere.
magari noi
Ciao.
ci sentiamo tra qui e il
Sì.
venerdì.
Mi dispiace Andrea che tutte le volte non ti si sentiva un grande eco.
Aspetta, ma perché
Ma
secondo me,
perché
Andrea,
Andrea è entrato con 2
ci sei 2
account.
volte.
Secondo me è
Sì?
per quello.
Ah, questo non lo sapevo.
Aspetta, che forse ti posso... Che forse io
Sì,
ti posso...
Riccardo, se me lo puoi disabilitare, almeno può parlare. Prima non si
ma...
sentiva.
ma non so come. Che spello, aspetta, che spello un Andrea Cantini.
Vai.
Proviamo.
Sei tornato solo. Infatti vedi ora
Oh.
funziona.
Ecco, no, infatti io non,
si sente.
ho tentato varie volte di parlare, però appunto con questo eco, come mai sono entrato con 2 account?
Probabilmente hai fatto la procedura 2 volte?
Può darsi, sì, può
Avevi
darsi.
aperto da 2 parti perché si poteva entrare o dalla mail o dalla mail potevi entrare o dal tuo account
Con l'app.
non so.
Vabbè, insomma, in ogni caso ora si sente bene e io sono stato trattenuto da parlare varie volte per questo enorme casino che c'era sotto. Comunque va bene.
No, comunque mi dispiace che il talk è stato lunghissimo e la prossima volta...
No, va bene. Ora infatti volevo salutarmi, mi fa piacere ora aver regolarizzato la situazione da un punto di vista fonico, diciamo, così almeno mi sentite e vi posso salutare, insomma. Va bene.
Bene,
Comunque, te che sei in Germania, ora verrai scambiato da Pierluigi che verrà su. Quindi,
Ah, sì?
dico, sì, no, lui però va su a Berlino, no?
Ah, sì. Ma perché passa le vacanze su?
Sì, penso di sì, penso stia su per un po'. Lo devi chiedere direttamente a lui, ma mi sembra sì che vada ora tra qualche giorno, va e poi tornerà dopo la Befana, insomma.
Capito.
Quindi è molto informato, vi potete scambiare anche le notizie sui vari protocolli.
No, poi qui in Baviera tra l'altro ci sono delle regole strettissime, tra l'altro abbiamo adesso il coprifuoco anche noi dalle 9, ci sono un sacco di restrizioni.
Comunque è una tragedia, non si può andare avanti così.
No, però oggi hanno iniziato, no, ieri gli inglesi a vaccinare, speriamo che insomma,
Sì, vabbè, speriamo funzioni, speriamo che funzioni. Va bene. Comunque è un buon paper, l'avete già mandato? No.
No, anche perché ci è venuto in mente recentemente che dovremmo forse rispostare alcuni pacchettini per renderlo più efficace.
Sì.
No. Comunque mi piace perché siccome c'erano diversi studenti che hanno fatto peraltro logica, 3 valori, clini weak, clini forte e quindi anche i paradossi, con l'aggiunta anche della parte soritica, insomma è carino, è stato un bel seminario da replicare in seguito.
Grazie.
Devi venire in mente una continuazione, insomma, qualcosa del genere. Va bene?
Ah, sì, allora, questo ce n'è.
Ci proviamo.
Vi saluto e basta.
Alla prossima, ciao, buon Natale, buone feste.
Grazie.
A presto.
Ciao, buon Natale. Ciao.
Ciao Andrea, ciao a tutti. Ciao Andrea, ciao Bea, ciao a tutti.
Ciao.
Allora, insomma, a questo punto saluto anch'io, saluto e vado.
Ciao, ci aggiorniamo magari da qui al venerdì 18.
Sì.
Vediamo.
Vediamo come procedere, magari incorporiamo qualcosina, comunque sì. Okay. Va bene, alla prossima, grazie ancora.
Ciao.
Ciao.